Before we begin, I want to acknowledge the land that I'm standing on right now, the land of the ANU, the traditional lands of the Ngunnawal Ngambri people. If you've ever been up to Namadgi National Park in Canberra, you might have been lucky enough to go and see these rock paintings on the wall at Yankee Hat. These are evidence that the land of Canberra and the land on which ANU stands has been continuously inhabited by one of the oldest continuous cultures in the world. That's the culture of Aboriginal Australia. And so I want to pay my respects to the elders past, present and emerging of the Ngunnawal Ngambri people who have protected this land for us, this beautiful country of Canberra, so long. If you're watching us from a different location, somewhere else in Australia, maybe you can think about and respond in the chat. If you're on a different country other than Ngunnawal Ngambri country, please let me know in the chat where you're joining in from. Perhaps you're somewhere else in the world. There's around the world, indigenous lands have been colonized, and in many places like Australia, those lands were never ceded. So let me know in the chat where you're joining in from. I'd really like to know. Yes, Philip, the slides are different to the ones on the course website. This lecture is not going to be a standard style lecture. Things will settle down a little bit more in coming weeks. Because this is sort of organization and contents, I'm going to be jumping around a lot. So I've got some slides of my own. I'm going to be using some other materials here and there. And as you saw, we're going to have Callum do some live coding for us later on. I'll make sure that any important material that we go through today is available to you on the course website. Okay, so, first of all, who am I? My name's Josh. I'm a research fellow at the School of Computing at the ANU. I'm interested in high-performance computing, parallel programming models in particular, so different programming languages that allow us to express parallel algorithms beautifully and, more importantly, efficiently. And I'm also interested in fault tolerance. That's great for me because this is the first time I've taught this course on concurrency, but it's really an area of interest for me. I love systems programming. I love the complexity that comes with it, and I love trying to find ways of dealing with that complexity, and that's what this course is all about. So I'm quite excited to be teaching this course. Z says YouTube seems down. Yes, I think I understand why that's happening, Z. For this lecture only, the YouTube will probably have to be done as a recording. Sorry about that. You'll have to watch on streams or Twitch if you're watching live. I assume if you're hearing me talk right now, you are. Right. So I really love this subject area. It's very exciting. But full disclosure time, until very recently, I didn't realize I would be teaching this course for this semester. It came as a bit of a shock. You may find a lot of evidence of this guy as we go through the course together and as we look at the materials. This guy is Dr. Uwe Zimmer. Uwe has been with the School of Computing for a very long time and has built this course up over a number of years to be a really interesting and really well-designed course. Now, unfortunately, Uwe is not able to lecture the course for this semester, so you have me instead. But you'll notice as we go through the materials that a lot of these materials were developed by Uwe, and I've as I say, I think it's a really well-designed course, so I'm not going to change too much, and we're going to be using a lot of what Uwe has created over the years. So, that kind of full honesty, I'm stealing Uwe's work, holus bolus. But it is really interesting material, and I'm looking forward to sort of exploring the material with you, and perhaps occasionally putting my own spin on some of the material. One of the really interesting things about this course that we'll talk about later is the use of the heavy use of the Ada language. And again, full disclosure, unlike Uwe, I'm not an Ada expert, and that's why I'm bringing in a slightly more experienced Ada programmer than me, Callum, who you saw earlier. Callum's going to help us out with some of the live coding exercises. Anyway, if you see on the website anywhere, you see the name Uwe, you'll know why that is. Okay, so first of all, I quickly want to go through sort of the mechanics of the course, some of the material that we've made available to you, things that I expect that you have already done or will do very shortly, just to make sure that you know everything that you need to do to get up and running with this course. So I'm actually going to jump over to the course webpage. Yes, Wenxi and others may have heard of Uwe's habit of using himself as a mouse pointer. Unfortunately, you won't see that from me this time. I'm a very boring lecturer. I'm just going to stay down in the right-hand side of the screen and not move around a lot. So I apologize for that. Maybe we can find some other ways to make things fun. Maybe we can all be mouse pointers at some time. Yeah, Shilong, yep. In terms of chatting, please just write your text chats directly into the lectures channel in Teams below as a response to the post that I made at the start of this lecture. We'll do that every lecture. I really want to hear from you all, and I'll be watching it as we go, and Callum will also be watching it and responding to you in the chat. And if you have a question, or if you see somebody else's question that you think you can answer, please give it a go. Please try and be helpful to your fellow students. All right, so let's jump over quickly to the course webpage. I just want to show you some of the material that's there. Hopefully you can see my webpage in front of you right now. Right, so got a really short list of the most important things that you need to do to succeed in this course. The first, of course, is attending the lectures, and we'll have lecture material made available after each lecture. As I get a little bit, as I catch up a little bit, I'll try and make as much of the material available before the lectures as I can, so that you can follow along with slides if you need to. And right away, I want to show you a resource that's going to come in really handy to you, which is the material from last year's version of the course. This is all available to you as an ANU student. You can see this if you're inside the ANU network on a slightly different location. So this server Varese is one that's managed by the School of Computing, and it's got the 2020 edition of the course. So that's all of the material that we've made available in the 2020 edition of the course. You've got lecture notes. For each of the lectures, you've got Uwe's slides. You've got recordings, both video and audio, for all of the lectures. And you've even got the older versions of the labs and the assignments, and you can refer to all of those. Some of these materials will be very similar for this semester, but if you ever need to refer back to what things happened last semester, you can do so. So I'll leave you that link to Varese. I'll actually just put that in the chat for anyone who wants to look at it. That could be a really useful resource for you. Again, that's only available from within the ANU network. So if you're outside of ANU right now, learning from home, you will need to use ANU's virtual portal to access those slides inside ANU. Okay. So while we're updating this semester's version of the course, I wanted to draw your attention to a few things. First of all, if you're interested in course policies on anything, organizational stuff, for example, how to talk to me. I'm really happy to engage in discussion with you during the lectures or at the end of the lecture. Most importantly, I'd like to make really good use of the class Piazza forum. So Piazza is a chat site, a forum site rather, and it allows us to discuss aspects of the course, and you'll find posts from me telling you about important current events, like you need to register for a lab, and we can discuss questions due to the course material here. So if you have any question about the course that's not specific to your own personal circumstances, please post it here on Piazza as a public question. If there are any questions about the course that are private in nature, for example, you're sick, you've got a medical issue or something, please also post it to Piazza as a private message to me, or if it involves your tutors, something about assessment, please post it as a private message to instructors. You can write a notice to instructors on Piazza, and that will go to me and all of the tutors, so we can help you with whatever the assessment issue is. But yeah, please use private messages only for stuff that's actually your own personal circumstances. Anything about the course, we want others to be able to see the questions you ask and benefit from the answers that we give. Okay, so that's the main way to communicate in the course via Piazza. There's a couple of things around assessment I want to briefly talk about. So this is the draft schedule for assessment of the course. Michaela's asking, what's the link to the 2021 course webpage? So that's the one I'm looking at right now. You should be able to find that at cs.anu.edu.au/courses/comp2310. I'll just put that in the chat as well. Okay, so those, you'll see those URLs are very similar, but this is the 2021 version of the page. Okay, so on assessment, this is the draft schedule for assessment. In week 4, we will have a lab hurdle exam, and the way that will work is you'll be required to complete the work for lab 4, and also have a short oral examination with your tutor, just so your tutor can check and make sure that you're on track with the basics of the course up to week 4. That's really not meant to be a scaring thing. If you're keeping up with the lectures and you've completed the lab materials by then, it should be fairly straightforward for you. We've got 2 assignments due in week 8 and week 12. Between them, each of those assignments is 15%. And between them, both of those assignments also constitute a hurdle. And then we've got a mid-semester exam, 15% again in week 6, and a final exam worth 50%. Of course, that's in the examination period at the end of semester. So that's the draft schedule for assessment. If you have any major problems with this, or you can see this isn't going to work, please let me know via Piazza as soon as possible. By the end of week 1 this week, that assessment schedule will be locked in. And I did want to draw your attention to this important policy about hurdles. So to pass the course, we have 3 hurdles. We have the final exam. You must score at least 40% on the final exam. You must score at least 40% on both of the assignments together, so a total across both assignments of 40%. And you must pass the week for hurdle lab. So 3 different hurdles for the course, and you must pass all of those hurdles to satisfy the course learning outcomes. Okay, so that's quite a lot of hurdles. That's perhaps that's unusual for computing courses, but with that, that's the number of hurdles that we have in this class. Okay. So, right now, as it stands, none of these assessments are redeemable. So what you get is what you get. And I guess it's important to notice some policies that I've written down here about deadlines. If you've studied with me in COMP2310, you may be relieved to know that my policy for this course is not going to be quite as strict. Yes, we have deadlines, we publish them ahead of time, and we expect you to submit your work by the deadline. If you have a good reason, and that's something that's very specific to your circumstances and you can't control, for example, some personal crisis or a serious medical issue, there are always chances to postpone the deadline for a reasonable amount of time. In really significant cases, you should consider applying for ANU special consideration. So if you go to this special consideration website, it will tell you what to do to apply for special consideration. So those options are always available to you. So although those assessments, none of the assessments are redeemable, special consideration may allow us to adopt a different grading policy in special circumstances. Okay. And yet, Chafu was just asking about the website. Just when you're consulting the website, make sure you notice you start at the one that says website for 2021. That's the way you know that this is current information. Please don't go off the policies of the 2020 version of the course, because policies may have changed slightly between now and the last time it was run. If you have any questions that are not answered on the website, please ask on Piazza. If you notice any inconsistencies or problems with the website, please let me know on Piazza. I want this to be as accurate and as easy to understand as possible. So please let me know immediately if there's anything strange there, and I'll get it fixed up. Okay. And finally, you'll notice there are some resources that are available. You probably want to consult, for example, you might want to get to know your tutors. So the tutors will have bios up here so you can get to know them. You may also want to know how to set up software for the course, for example, installing tools for Ada development. And we've got a link here that takes you to the community edition of the NAT Studio, which we're going to be using for Ada development. And there's also a list of helpful references here, including the course textbook and other references around languages. Now, we say this is the textbook. This is Principles of Concurrent and Distributed Programming by Ben-Ari. You can actually complete this course without the textbook. The course does not follow it too closely. So I understand that it's an expensive textbook. I don't think you will be significantly disadvantaged if you don't buy the textbook. So please don't go and spend your hard-earned cash on this, assuming that you need it to complete the course. You do not need it to complete the course. All the material that you require will be made available through the lectures and the labs and the assignments that we provide. Okay, I think that's all I wanted to cover in terms of course organization, but are there any questions that you have right now? Patrick asks, so does the content differ greatly between 2020 and 2021? No, as I said, I'm going to follow Uwe's course structure very closely. So you can imagine that the material you find on Uwe's 2020 version of the site will be pretty close to what we're going to be working on this year. There are some differences, mostly presentational. So for example, you'll notice that we've moved to a bit of a different structure for labs. In the past, you would download some code as a zip and follow through a PDF document of instructions on how to work with that, and then submit it through an application called the submission app. This year, the instructions are all available to you as a web page, and so here's a web page that I've prepared with the help of one of our tutors, Felix. So this web page gives you all the instructions for the lab, and the actual lab source code itself is going to be available to you through GitLab. So I'll just go down and follow the link to GitLab, and you can see this should be available to you now. There's a GitLab project for the first lab for this course. That contains some Ada code in a Ada project, and you can just fork and clone this repository and then work with it locally using NAT Studio. Okay. Haoju asks, so we don't have a hurdle on midterm exam? No, that's correct. There's no hurdle on the midterm exam. Z points out we can access an ebook of the Ben-Ari textbook at the ANU library. That's fantastic, Z. That's very useful, obviously, if you're not physically here and therefore unable to actually borrow the physical book. So it's good to have that ebook at ANU library. Shulong asks, are we using Ada instead of ARM now? Yes, although this course follows on from COMP2310, we're not going to be programming in assembly, and we're not going to be using ARM assembler in this course. We're going to be primarily using the Ada language. We will be using some other languages as well. I want you to realize this is not a course about a language. It's not a course about Ada. It's a course about concurrency concepts. Ada is just the vehicle that we're using. Thanks, Angus. I can see people starting to answer each other's questions in the chat, which is great to see. Okay. On the software setup side, I did want to draw your attention as well to the fact that, as usual, we do provide a lab computing environment. So if you're physically in Canberra, obviously you can come to the School of Computing labs where the software for development is already installed on those computers. If not, we do provide the same environment through the virtual desktop infrastructure, and there's some notes here about how to access that. I know that this tends to be quite difficult to use if you're working remotely and you have poor internet speed. So this may not be a great solution for you if, for example, you're on a different continent. In that case, probably your best option is to install the software locally and work locally. And so we provide this link to the NAT Community Edition, and we also provide a link to install the Chapel language, which we'll be working with later. So install the software locally, and you can work through GitLab. We've found that that combination of local development plus Git tends to work pretty well even when you have poor internet connection. So hopefully that will work for you. If you have any technical issues, again, please raise them on Piazza and we'll try and help you work through them. And this is probably a good time to make a plug for the Computer Science Students Association's Install Fest. I believe that's this Thursday. Anyone from the CSSA here in the chat who can confirm the time of Install Fest this week? Okay, I believe it's Thursday afternoon. So yes, get onto the CSSA website and find out the time of Install Fest. They can help, the volunteers at Install Fest can help you install the software for this course, including NAT Studio if you need any help. Thanks, Leopold. It's Thursday, 5:30 p.m. physically in N101 in the CSIT building. And I don't know if there's going to be, I believe there's going to be an online option as well, right, Leopold? Okay. Cool. All right, let me switch back to my slides. I think we've gone through all the course mechanics that I wanted to go through. I just wanted to point out to those of you who may not have seen this before, ANU has a access and inclusion unit. The role of this unit is to help you as an ANU student access courses where you might not otherwise be able to due to some of these issues mentioned on the screen, like a physical or learning disabilities or current medical conditions, ongoing medical conditions, and also if you happen to be an elite athlete have a more active role in your education. So I'd encourage you, please, if you think this is a role you could play, please put up your hand as a course representative. And the way to do that is simply to send a private Piazza message to me, just letting me know that you would like to be a course representative, a little bit about yourself, so why you want to be a course representative and what your background is, if you're in terms of earlier studies. And then I will pass your nomination on to the Associate Director of Education so that you can represent your fellow students. So please message me in Piazza if you'd like to be a course representative. In the past, course representatives' feedback has managed to rescue failing courses where there have been significant problems, and course representatives have identified them and worked with the convener and other staff at the school to help turn things around. So it's a really important role. Okay, all right, we already covered hurdle assessments. Just a quick thing on plagiarism. You've probably heard this a million times before, but I just want to go through my expectations on plagiarism or on academic integrity. It's very important to us at ANU, and it's very important to me in this course that both I and all of you behave with integrity. What does that mean? It does not mean working alone. It does not mean relying entirely on your own resources. Research, finding information out from elsewhere, and collaboration, working with others, these are good things, and I want you to do that a lot in this course. So do those things, collaborate and be resourceful. The main rule that I want you to follow in this course, when you're submitting assessment items, and in general elsewhere, is please don't represent somebody else's work as your own work. That's really what the main rule is. If you're drawing on someone else's work, say so. Reference them, give them appropriate acknowledgement. In fact, here's a good example of it. This entire slide, I think, just about this entire slide, I stole directly from Professor Steve Blackburn. So these are his words. So please, when you're using somebody else's work, and it's important, make sure that it's clear that it's somebody else's work you're using. In most cases, if you do that, there will be no negative consequences to that, and in fact will hopefully be impressed by your appropriate and mature academic behavior by referencing somebody else's work. If any of that is not clear, please go and read the ANU's position on academic integrity. It's quite detailed and it lays out the principles that we operate under at the ANU. Any questions on any of that? Okay, so I think, oh wait, I just need to scroll down to the bottom of the chat because I realize I'm well behind. Oh, thanks, Saffron. But Saffron points out that the Disability Students Association is having an Access and Inclusion Help session this Thursday lunchtime, 12 to 1 Canberra time, and that'll be online via Google Meets. Okay, so perhaps go look up the ANU Disability Students Association for more details of how to get into that event. Thanks, Saffron. Mungchi asks, can we refer the idea? Can you refer to other people's ideas? Yes, absolutely. In fact, we expect you to do that often. That is good academic practice. To use somebody else's idea and to reference them correctly is good academic practice. When she asks, is it possible to use Ubuntu to do the labs and assignment? Yes, absolutely. You can install all the software that's necessary for this course on just a regular Ubuntu instance and you can work with it. Oh, and thanks again, Saffron. Saffron says, if you want to know about the Disability Students Association event, just message Saffron directly. Thanks. Shilong asks, do we need ADA basics for this course? Yes, and that's what we're about to get into. So we've had Callum waiting here patiently. He's going to help with some live coding in just a few minutes. So we're actually going to go through the basics, some basics of the ADA language this lecture, and we're going to do some more next lecture. Because I realize very few people in this course have probably ever seen, let alone coded in the Ada language. And so we're going to try and work through the basics right now. Okay, so what is Ada, first of all? Ada is quite an old language now. It was first developed in the 1980s around the US Department of Defense. But it's evolved a lot since then, and there have been several major releases. So it's a very well-established, standardized language, and it has both free and professionally supported. So commercial versions of Ada compilers are available for pretty much every major OS, and that includes, most importantly for all of us, Windows, Mac, Linux, Unix platforms. You should be able to find a version of a free Ada compiler. And just to remind you that there is a free Ada compiler, the NAT Studio, or GNAT, the compiler, that's linked to from the course website under resources. Okay, so what's the purpose of Ada? Well, it's designed for developing maintainable, high integrity and efficient systems. And think the kind of runtime environments for embedded systems in highly high risk environments like aviation, like automotive, like military systems. This is the sort of thing it was designed for in the first place. So you will find Ada used to develop systems that are running inside things like flight control systems in planes. And as part of that, there are what are called profiles of Ada, so subsets or smaller language descriptions based on Ada that are part of the standard. And so there was, for example, the real-time profiles like Ravenscar that are designed for developing real-time embedded systems. So Ada is used in a lot of very large-scale, high-integrity projects, as I mentioned, like aviation. Also high-speed trains, metro coordination systems, even in the space program, and as I mentioned as well in the military. So if you're interested in working in any of those industries, you may well find that you'll end up using Ada. If you haven't worked in any of those industries, like I haven't, then you may not have a lot of experience with it yet. But that's okay. What we're going to do right now is go through some of the basics of Ada, and we'll hopefully demystify some of it. Okay, so I'm going to switch slides again. We're going to go over to Uber's slides. And as I mentioned, a lot of the time I'm just going to steal Uber's work directly. You'll see his copyright notice on a lot of these slides. There are some good reference manuals. Another thing that's not mentioned on this slide is Learn Ada Core, which is a nice collection of basic tutorials for Ada. I'll actually put that up as a reference on the website. But for now, a couple of other features of Ada that are quite interesting. First of all, this is just a quote from the ISO standard for Ada. Ada is intended as a general purpose language with a focus on program reliability and maintenance, programming as a human activity, and efficiency. That does sound like Department of Defense speak, but I guess the important thing is it's not strictly intended as a real-time language. It's not strictly intended just for aviation. It is intended as a general purpose programming language like C or Java or something like that. But the important part is this focus on reliability, and we'll see how that comes across in some of the features of Ada. The reason we're using it in this course is, well, a couple of things. First of all, it provides some very interesting language primitives. In particular, it provides a very strong type system that allows you to constrain the types you're operating on in a number of interesting ways. It provides all the usual kind of structured programming support that you've come to expect from modern languages, like abstract data types, like generic types and object orientation. But importantly for this course, it provides some very interesting language primitives for concurrency. And it provides things like message passing and synchronization primitives. It provides a very interesting primitive called a monitor, or in Ada it's called a protected object, but we'll go into that in much more detail. And it provides some interesting things around timeouts and scheduling that you can use to build systems working in real time. And it provides some very high performance, reliable runtime environments. And there's some additional annexes, so these are sort of optional add-ons to the language around real-time features or distributed programming. Some of these we won't go into much in this course, but it's interesting to know that they're there. Okay, just quickly checking the chat. Trisha asks, will I be making the slides available before the lectures in the future? These slides, Trisha, are all available already on UVA's website that I showed you just earlier. So if you want to look at any of UVA's slides, you can go and download the whole course worth of slides already. For any slides for additional material that I provide, I will make them available hopefully before the start of the lecture in the future. Apologies for the rushed start to the course. Okay, and Ben's answered Angus's question. From the point of view of this course, we'll primarily be working with and testing our materials against the GNAT Ada Compiler Community Edition. So you're welcome to try other tooling, for example, the Ada compiler built into GCC. You're welcome to try and use those. We don't make any warranty that for example, the projects we provide to you are going to work with those tools directly. You may have to do some extra work yourself to get things working. So we test and we will provide you with support for GNAT Community Edition because it's free and available to you. Okay, so we're going to go through a really quick crash course in Ada. We're going to take you through some of the basic features of Ada. An interesting feature that you may not have come across in other languages like Java is that Ada is very strict about separating out code into the specification, so that effectively the interface of a piece of code, and the implementation. We've got used to thinking in this way in other languages, but Ada actually separates them into usually separate files. So for those of you who are used to C++, this may not be so unusual. For those of you coming from a Java land, this may be the first time you've seen this strict separation. We will go through exceptions. Ada provides exceptions that are probably familiar to people who've used Java or C++ exceptions. We'll look at how to hide information inside a specification. So this is about encapsulation, a really important part of structuring your code to reduce the complexity and to ensure that you don't code up a piece of spaghetti where a change in one place can have dire, drastic consequences somewhere else in your code. We'll look at a really interesting feature of Ada, which is contracts. So contracts allow you to specify the invariants that must hold at various points in your Ada program, and to have the Ada system enforce those invariants for you. This is a really good feature if you have some safety critical property of your system that needs to hold. You want to know when that property fails to hold. So we'll look at how to represent that in Ada. We'll look at generic programming. Hopefully this style of programming will be familiar to you. Polymorphism, where you have a piece of code that is able to operate over many different types. And we'll start to look at some of the concurrent features of Ada. We may not get to this today, but we'll get to it in the next lecture, like tasking, how to create concurrent tasks that operate at the same time, how to synchronize between those tasks in a way that prevents them, two tasks accessing a critical piece of data and updating it and causing problems. And then we might look at some more advanced features of Ada, like abstract types. Ada is a very large language. It has a lot of features. We're not going to demonstrate all of them here. We may not need all of the features of Ada for the course. Think of it like C++. But one of the reasons that we are using Ada for the course is it has this range of different concurrency primitives, both low level and high level, that will allow us to demonstrate and explore many of the concurrency concepts that we're going to go through in this course. I'm not saying it's the best language for concurrency, but it is quite a rich language and it will allow us to go a very long way with the material. Okay. So to start with, to motivate our live coding exercise that Callum's going to take us through in just a second, I want you to think about a relatively simple data structure, which is a queue. How would you implement a queue? So a queue is a thing, a data structure where you add things to one end of the queue and you remove them from the other end of the queue. Just like in real life, when you queue up at a shop, you join the queue at the end and you move forward through the queue until you reach the front of the queue, and then you're removed from the queue as you're served by the person in the shop. Okay, so this is the data structure that's common in a lot of scenarios. It's very useful. How do you actually implement, let's call queue the abstract data type. How would you actually go about implementing the abstract data type of queue in a concrete way? What sort of data structure would you use to implement a queue? So you can see a few different options here on the screen in front of you. Maybe you can think of some more. If you can think of more, please put them in the chat. There are perhaps, if you're coming from a dynamically managed environment sort of language like Java, maybe this one on the left seems most natural to you. We might construct a data structure that looks maybe like a doubly linked list, where each element of the list contains a value that we put on the queue, and every time every element is going to link to the next element and the previous element of this linked list. And then our operations become relatively simple. We probably need a pointer that tells us where the start and the end of the list are. And when we enqueue, we'll enqueue to one side by creating a new element in the linked list and linking it up with what used to be the first element of the queue. And when we remove an element from the list, when we dequeue, we can simply take the value of that element. We can remove that link that was created between the last element and the one before it, and then the one before it becomes the last element of the queue. Okay, so this is a very dynamic structure of queue. What are some advantages of this structure? Well, it's easy to see how we can grow this queue. We can grow it as much as we like, and we can shrink it as much as we like just by dynamically creating and destroying these elements of the linked list. So that seems really nice. What are some disadvantages to this queue structure? Thinking about if you were working in a real-time environment or a resource-constrained environment, all of these elements of the list need to live in some heap data structure somewhere. So, in a language like Java or in C++ using a new delete style of allocation, these are being allocated somewhere in the heap, and the cost of allocating and deallocating these elements may be non-trivial. In Java, you may have garbage collection, for example. So the result of all of this is it may not be immediately apparent how long operations on the queue take to enqueue and dequeue. There may be some sources of non-deterministic behavior in there in terms of timing. Yeah, it could be inefficient. Yeah. Okay. So we've got some options, some different kinds of options for implementing a queue, and some other ones might be something like a fixed size buffer where we have one end is in and the other end is out, and we might do something like, for example, every time we add an element to the list, we move all the other elements. Sorry, add an element to the queue, we move all the other elements down by one, or something like that. So we have an absolutely fixed amount of memory associated. We don't have any memory required for pointers or anything like this. So in that respect, it's very space efficient. The disadvantage of what I just described might be that you're now doing a lot of moving of data around as things move through the queue. And so maybe a a halfway point in terms of efficiency between these two could be something like a ring queue. So here we have, on the right hand side, here we have a queue that is implemented still over a fixed length buffer. So we have a fixed number of entries in our array-like data structure, but we have 2 pointers to the start and the end of the queue. So where we're going to enqueue and where we're going to dequeue elements. And all we need to do whenever we add a new element to the queue is we move that enqueue pointer by 1. So we fill in a new value and then we move the enqueue pointer to the latest value that we filled in. And when we dequeue, again, we just need to remove a value and return it and move the dequeue pointer by 1 every time we remove something from the list. So we still have a problem of what to do when we run out of space. If we have used all of the slots in our fixed size buffer, we have to do something. Either perhaps we could throw an exception to indicate that we've run out of space. Perhaps we could do something like block and wait until space becomes available. And we could implement a similar kind of arrangement in a slightly more dynamic form. So here we have a representation of a singly linked list, but again with a fixed number of slots, and each of those slots is either full, in case here it's got a color, or it's empty if it's white. And again, we just have pointers for enqueuing and dequeuing that we move around. Okay, so these are some different options. So Angus is pointing out, I think probably in relation to these two implementations, the linked list options, I think Angus is pointing out that these would potentially have poor memory locality. That's a really good point. If you think about how this would map to cache, it's very unlikely that all of these elements have been allocated contiguously, one after the other in memory. What's far more likely is that they're allocated all over the place in memory. And so if we were to iterate through this queue, reading one element at a time, we're going to be reading from far distant points in memory. So that might not map very nicely to cache. So that's a really good point, Angus. Thanks. Okay, so we're going to implement a queue data structure in Ada. And we're going to go through a number of different versions, but at this point I'm going to turn my slides off and I'm going to throw over to Callum, who hopefully is still there and we haven't lost him. Hey Callum. Hey Callum, can you hear me?
Hello Josh, I can hear you just fine.
Great.
Can you hear me?
Hear you. Okay, hopefully this will work okay. So I'll get you to share your screen, because I think the first thing we want to do is actually show people Nat Studio.
Cool. I should introduce myself real quick.
Yeah, please do.
Yep. Hi everyone. My name is Callum. I have been a tutor at the ANU for a while. This is my 4th year tutoring. You may have recognized me from COMP2310. I'm currently an honors student. I'm working in high performance computing. That's about making computers go really fast. So I think about things like assembly programming and CPU hardware and concurrency on a daily basis. I've never presented to such a large audience before in my tutoring career. So I'm going to take advantage of this opportunity and say that if I have one piece of advice to help you get through this course, it would be to listen to Taylor Swift's album Evermore. I think it will be really helpful for you. So shall we get started, Josh?
That's great advice. Yes, let's get started.
Right, yeah. So the IDE we're using for this course is called Nat Studio. I'll just boot that up here. So the first thing we're going to do is create a new project. And this is really simple. You just do the obvious thing. You click Create New Project. Then you look for Simple Ada Project, and you open that up. You can give your project a name. We're going to be implementing a queue, so we're going to call our project Queues. And our main program, we're going to call it QTest, because it's going to be testing our queues. And then here we have it. It gives us a relatively blank file with a main program for us called QTest. Yeah, so in Ada, procedures which are effectively a special name for a void function, a function with no return value. This is the rough syntax for them. It starts with procedure, then you give it a name, and then you have the is keyword. And then your code goes in this begin end block right here. The really nice thing about this that I really love is that there are no curly brackets involved. No ugly curly brackets, everything is begin, end. Right? And so make a type to represent the queue itself. And declaring a type is as easy as just type QType is, and then you have something to define the type. In this case, the queue itself is going to have some amount of data associated to it. Maybe an array, maybe a linked list, maybe some pointers or values or things like that. And we can capture all of that stuff in a record. So let's make a record type for this. Just like that. And then inside here, we can put all of the record fields that we want our queue to have. But I will defer filling out the body of that for now. We'll leave this for later. And let's...
So Callum, is a record maybe like a struct in C? It's an object that has a number of fields, not necessarily any behaviors associated with it?
Yep, a record is just a collection of some amount of data. I would be hesitant to describe it as like a struct because I don't think people have seen C. But for those who have seen C, it is exactly a struct.
A collection of data. That sounds good.
Yeah. So, like, you might have an integer in here. You might have some other things in here. I can't think of. Well, you might have a string or something, right? And then something of type QType will have all of these things associated with it. So we might put in things like arrays or other stuff like that later. But yeah, thanks for bringing that up, Josh. And so let's think about what do we want to be able to do with a queue. There are two fundamental operations when it comes to queues. We want to put things into the queue, and we want to take things out of the queue. And for that, we would like to have two operations. enqueue to put things into the queue, and dequeue to take things out of the queue. These procedures are going to need some parameters. So they're going to be operating on a queue. So we need to put a queue into the procedure. And for enqueue, we're also going to need to put in an element to add to the queue. Now, I've referenced this type here, element. I haven't discussed that yet, but the queue that we're making, it's going to need to have some kind of type to represent the things that it holds. It might be a queue of integers, might be a queue of strings, etc. Later on, we're going to use generics to allow our queue to hold any type of things that we like, but for now, we're going to constrain ourselves to just a single type. So let's declare the type of elements we're going to be using. Now, we could put any type here that we want, really. For example, we could say that our elements are integers, or our elements are strings. We could also have some kind of, well, we can also have subtypes of other types. For example, you can have a particular range of integers. So this declaration here we're declaring a type element that is an integer range from 100 to 1000. So if something is of type element, you know that it's an integer lying between 100 and 1000. If you tried to make an element and make it equal to 99, the compiler would throw an error saying 99 is not a valid value for type element. If you do 100, then that's fine. The value of range subtypes like this is not immediately obvious, perhaps, but throughout the course we'll see that they can be quite useful. Yeah, so we'll just leave it at that for now. We've got a question.
Do integers need to be constrained between two values? That's from Angus.
Well, sort of necessarily, yes. Between, negative 2 to the 31 and 2 to the 31, there is some fundamental limit from the architecture you're using, unless you've implemented some kind of extended precision integer type yourself. But we could just have type element is integer, and that would give you the default sort of integer on your system. You don't need to specify bounds for it.
Maybe to get us thinking in an Ada way, if you don't specify the bounds, then you'll get those default integer bounds, and things may happen like if you add together two really big numbers, you get an overflow and you actually end up with a negative result. Can you think of any good reason why you would not want to constrain your integers? Like why you would want to get the default architectural overflow? In general, that seems like that would be an unsafe and a bad thing to do.
Yeah, that's a really good point. Ada-style programming is all about being incredibly specific as you possibly can be with your types. I
asked a really good question. So before you used a function, you wrote a function and you used the keyword function. This time, now we're defining things called procedures. So what's the difference between a function and a procedure?
Well, that's a good question, and it's really simple. A procedure is a void function, a function that doesn't return anything. So when you have a function of some kind, you need to specify it returns some kind of value, right? But if you want your function to return nothing, I guess you could put void in there or something. I don't know if Ada has a void type, how you would expect, but a procedure is effectively a function which returns nothing. And also, by convention, functions are generally side effect free. So if you, and procedures are allowed to be side effecting. So for example here, in the dequeue method, we could have this as a function that returns an element, right? But this function would be side effecting because it takes in a queue and it's going to remove something from that queue. And because it's side effecting, we will, instead of phrasing it as a function, phrase it as a procedure. And rather than having a return value, we'll give it an out parameter. If that makes sense. Does that sound reasonable, Josh?
That sounds really good. So this out keyword is an unusual feature of Ada that people might not have seen before. That you can have parameters that are passed in as values, parameters that are only used like a return value, in which case we label them with out. And you can also have parameters that are used both ways. They're copied in when we call a procedure, and they're copied out again when the procedure returns. Yeah, this is an unusual feature of Ada. Maybe compared to your own favorite language, that you're most familiar with, how are parameters passed in other languages? If you use Java, how are parameters passed in Java? And how is that different in Ada?
One important point about Ada is that everything is passed by value as default, unless you explicitly pass a reference. So when we pass in a queue type right here, this is going to be passed in by copy. It's going to copy the entire queue into the procedure, and the procedure will be working with that copy. And this holds true for things like arrays as well. Arrays are passed directly by value, copied into the function, unless you explicitly pass a reference instead. Got some questions? What if we use integer directly as a type for item? Is it possible to do so? Yep, we could do that. There's nothing stopping us from doing that. We could just say type element is integer. We could also just use integer down here instead of element. Yeah, we can use that type however we like. It seems we can control the way we pass and get parameter in Ada. Yep, we can. Primarily through these in and out keywords. How do you make it pass by reference? Do you need to change the type signature? Yes. We won't cover these yet, but there are explicit reference types. You can have a type which is a reference to an integer, and then you could pass that in. What's the difference between using out and returning something? The difference is pretty subtle. So if, for example, DQ returned a value, you could do x equals DQ from the queue, like that. But in the case that we're using an out parameter, we would do DQ x q. So functionally, there isn't really a difference. Like, you can accomplish the same behavior by just writing things differently. You can have multiple out parameters rather than just a single return value from a function, but functionally you aren't really limiting yourself by using either a return value or an out parameter. Does the keyword out do the same thing as the keyword out in C#? Yes, it does. If my C# knowledge serves me correctly, yes, it does. I haven't thought about that language in 8 years, but I think so. If we're using the second way, should we declare x first? Yes. You always need to declare variables before you use them. I wasn't being super thorough in my example code there. If we want to pass by reference, we need allocate a memory space for that and pass that. You need to have something to reference before you can have a reference to it, right? Unless you pass in a null pointer, I guess, but that would probably crash your program. So, yep, you will need to allocate space in some way. But that'll normally just be by declaring a variable and then taking a reference to that variable. Which way is side effecting? Well, remember that a function is side effecting if it changes something in your program. So if your function just takes in some inputs and maps them to some outputs and will have return the exact same thing every time you call it with the same parameters, then that is a pure function. If your function actually changes something, for example, if we pass in a queue and it removes something from the queue, that is a side effect. It has changed one of the input parameters. It has changed something in your program. Whereas a non-side effecting function doesn't change anything. Pass by value prevents side effects. Yes, it does. Generally, passing by value will prevent side effects, unless you also then pass out by value. So there is, you've got your in parameters and your out parameters. You can also have in-out parameters, which are passed in by copy and then passed out by copy at the end. So you can still have side effects when passing by value, but through passing out by value. There are also other ways of accomplishing side effects with pass by value, but yeah.
Okay, so Callum, because we want our enqueue and dequeue operations to modify the queue type, if we want those modifications to be visible, we actually need to make it in-out. Is that right?
Yeah, you're correct there. So as it stands, this queue here is just going to be passed in, but isn't going to be copied back out at the end. So if we pass in a copy and then remove something from that copy, the original queue won't be affected. So we won't actually have taken the item out of the queue. So Josh is correct here. We do actually need to pass the queue out at the end. But the queue is also taken as an in parameter, so it needs to be both in and out. And yeah, in this way, we can pass the queue in as a parameter and get the modified queue out at the end. What does the in keyword do? So the in keyword passes the value in by copy, but that is also the default parameter passing mode. Yes, Angus is correct. Parameters are just in by default. So here we've got enqueue item of type element. This is exactly equivalent to in element. Rightio. That's been a lot of questions about these 5 lines of code, but it looks like we're just about ready to move on. So we've got the type signatures for our enqueue and dequeue. We've got our element type, and we've got our placeholder for the queue itself. So next up, let's think about some functions that we might like to have associated with our queue. What are some side effect-free operations that we might want to perform on our queue? Well, there are 2 obvious ones. First off, we want to be able to tell if our queue is empty. So if our queue is empty, we obviously don't want to dequeue from it, because that's going to give us some horrific invalid values going on. Things might get broken. So we want some way of checking if our queue is empty. And that'll take in a queue. Oops. And we also want a function to tell if the queue is full. Oh, and I'll take this moment to demonstrate one of my favorite features of NetStudio. So see this line here is off in its indentation. Let me just go through and mess up the indentation a bit more. Sorry if this hurts to look at. So say hypothetically, you've got some code that's horrifically indented. NetStudio has a feature where you can click on a line and press the tab key, and it will automatically move that line to the correct indentation. And you can even highlight a region of code and press the tab key, and it will automatically indent the entire thing for you, which I think is a great feature, and I use it a lot. But, okay. So we've got some operations that we want to be doing on our queues. Now let's think about what kind of data we might actually want our queue to hold. So remember what we're doing here is a kind of ring buffer queue. What it's going to look like is we're going to have some empty, or some array underlying the queue. If you will take this sequence of dots here as an array for the purposes of demonstration. And when we put something into the queue, we want to add it to the first free space, like that. And then when we enqueue, we want to add and add and add and add, like that. And when we dequeue, we want to start taking things from the beginning. So we could dequeue that element, then dequeue that one, and dequeue that one. And then we might want to enqueue some more and dequeue some more. And this is the important part here, is that if we keep enqueuing and we get to the end, it then wraps around and the next element gets enqueued at the start, like that. And so we can keep dequeuing and we'll come back around to the start and start dequeuing from there. I hope that demonstration made some sense. It would have been nice to have like paint open or something, but I hope this ASCII art demonstration worked fine. But so, what do we need to do this? First off, we need our underlying array. An important feature of this design is that the queue has a fixed size. So we're going to want a constant to keep track of that. We'll call that constant queue size. It's going to be a constant. And the type we're going to use for this is positive. So we could have the queue size as an integer, but integers are allowed to be negative numbers, and it wouldn't make a lot of sense for us to have a negative length queue. So instead of integer, we're using this type here, positive, which is effectively the set of positive integers. So if I tried to assign this to be equal to -1, the compiler will complain and say, hey, -1 is not a positive value. So we constrain ourselves to make sure that our queue size is going to be positive. There are other fun integer types that we have. So for example, we also have, positive, which is like 1, 2, 3, etc. We can also have natural. Natural is similar, except it starts at 0. Sorry if that offends any mathematicians in the room. Okay, some good questions in the chat. From Callum and Aaron, is it possible to have a queue size of 0? Or do we not want a non-negative rather than positive? Well, what's a queue of size 0? When are you ever going to assign a queue of size 0? Is my question. That's sort of like, you might be able to argue that technically a queue that cannot take any elements might technically be a queue, but it's certainly not functionally a queue. It's sort of a weird degenerate case. Like when there are no elements in the queue. So remember here we aren't talking about the number of things currently in the queue. We're talking about the maximum size of the queue. So this queue size here is a constant, and it's going to be the size of the underlying array, not the number of things currently in the queue. Constant means static final. My Java lingo is not super good. I'm sure Josh can answer that. But that sounds roughly correct.
Right. In Java, you would say something is static final to make it a constant. In Ada, you just say it's constant.
Yep.
Easy.
Cool. Static final. That's fine. And so we're going to need our underlying array for our queue. We're going to call that array elements. Now, what is the type of this array going to be? Well, as usual, we can just make a new type. One moment. Yeah, the really fun thing about arrays in Ada is that they aren't necessarily zero indexed. So in basically every other programming language that I know, if you make an array, it starts at 0 and goes up to whatever you want it to go by, and you index it with integers. In Ada, you define arrays by passing in an index type. So say we want to define a type for our array. We can do type is array range 0 to qusize of element. And this here defines a type that is arrays which are indexed in the range from 0 to this qusize we've given. So 0